Okay, folks, so this video might be a little bit long, but what it's going to be is a video solution manual for the review that you've been given for your quiz on August 21st, 2020, covering the first 3 sections of your McGraw-Hill pre-calculus textbook. Please make sure you've read the directions on the page and notice that these 6 different problems that we're going to look at represent an easy, a medium, and a hard version of each of these questions. Now, the reason why that matters is because if you can get the easy questions correctly, well, you'll probably end up with about a C on the quiz. If you can get the medium problems, that'll separate out the people that should get B's. And if you can get them all, that's how you're going to earn an A. Guys, you have to remember you are in an advanced math course now, okay? You know, getting a C in this course is going to be impressive because you will have done good hard work. Okay, you're doing hard mathematics. You have to persevere, you have to work hard, and you have to study. So I made some mistakes on the solution manual that I posted earlier. I've fixed those mistakes and I've reposted the solutions in a better situation, but I'll try not to make those same mistakes here as we go through this solution manual. It is rather late at night and I'm getting rather tired. So if I make a mistake, I apologize, but I don't think that I will. So here we go. When we are asked to evaluate a function, again, this is a review. We've already been quizzed on this once. We're still trying to prove mastery. So what we do for f of -3 is very simple. We plug -3 into the equation everywhere there is an x. So that would be -3 squared minus 3 times -3. And where I screwed up before is I forgot the plus 1. So we simply are going to simplify that as much as we possibly can. That would be positive 9 for -3 squared. Then -3 times -3 is another positive 9. And then we have a positive 1, meaning that f of -3 is 9 plus 9 plus 1, or 19. For letter B, when we plug into g of x, we are going to plug in 2m for x. So that's 2 times 2m plus 3. We can't do a whole lot to simplify that. We're simply going to do 2 times 2m, which is 4m, plus 3. Those are not like terms, so we cannot combine them. Finally, on the third one, h of 2a minus 1. This is an example of a harder one because we end up with a binomial 2a minus 1 squared minus 2a minus 1. So when we square 2a minus 1, remember that that is 2a minus 1 times 2a minus 1. So we have to FOIL that out. That would be 4a squared minus 2a plus 1. That factors out into 4a squared minus 4a plus 1. Then we have this -1 that we're going to distribute through the second set of parentheses, giving us minus 2a plus 1. Final step then would be to combine the like terms. The -4a and the -2a would get combined, and the 2 positive 1s would get combined to give us a final answer of 4a squared minus 6a plus 2. On number 2, we are asked to determine the domain of the function, which more or less means we're looking for values that are not in the domain. Okay? So for letter A, we need to remember that the denominator, x minus 2, is not allowed to equal 0 because we're not allowed to divide by 0. We simply solve that equation by adding 2 to each side. That tells us that x is not allowed to equal 2. Every other x value other than 2 would definitely work. So if we were drawing a number line picture of the domain, it would include literally every x value, every single one, except for 2. Which means when we write out the domain in interval notation, we have to include every number from -infinity all the way up to 2, and every number from 2 to positive infinity. So there's your domain for the first one. The second one is a little bit harder. Again, the denominator, x squared minus 5x minus 14, is not allowed to equal 0. So what we would think of that is we need to think of it in terms of factoring. It factors into x minus 7 and x plus 2. Those values are not allowed to equal 0, which
means x minus 7 is not allowed to equal 0. X plus 2 is not allowed to equal 0. So x can't be 7 and x can't be 2. Now later on we'll discuss how one of those values is an asymptote and the other value is a whole, but for now we're only interested in writing out the domain. So again, you should visualize a number line in your head, -2, not 2. There are two values on that number line that are not allowed to be in the domain, -2 and +7. Every single other x value between -2 and 7 and on each end is fully acceptable as part of the domain. So your domain here would have three pieces. We would have negative infinity all the way up to -2. That's this piece here. We'd have the piece in between, so and -2 to 7 here, and 7 to infinity. Notice how we have all open circles in our domain.
Okay, letter C is tricky because we need to remember that anytime we have a square root, the value underneath the square root has to be greater than or equal to 0. So we need to think about the graph of this parabola, the related parabola, x squared plus 4x minus 21. Again, if we factor that trinomial, we can discover that the roots of that trinomial are x equals -7 and x equals 3. And what that means is if we're looking at a graph of that parabola, we know that that graph opens up because a is positive, and we know it crosses the x-axis at -7 and +3. So it looks something like this. Would be the graph of the related quadratic where we're at -7 and +3. So then the question arises, because it's an inequality, because it's greater than or equal to 0, we're supposed to either shade inside or outside. And we don't know which one it is. So what we do is we pick an easy x value, like x equals 0, and we test the quadratic. So we say, okay, does 0 squared plus 4 times 0 minus 21, is that greater than 0? So we're testing this point in this inequality. If that statement is true, then we would shade the inside because x equals 0 would be shaded. If this statement is false, we would shade the outside. So that is a false statement because that ends up being -21 is greater than 0, which is a false statement. Now what that means is that we're shading the outside, which more importantly tells us that the domain of our function is outside of those two values. Okay? So the domain of our square root function only exists when x is less than or equal to -7 and when x is greater than or equal to 3. So in terms of thinking of it as a number line, we have closed circles at -7 and 3, and we are shading out. So our domain would be from -infinity to -7, including -7, so a square bracket for -7, and 3 to infinity. That's a very difficult domain to come up with, so hopefully that made sense. On to number 3, where we're given graphs and asked to find the domain and range. Again, this is a very sticky, it's a very difficult concept, okay? But keep in mind that it's all about looking for where the function goes. So if you look at the first function, letter A, that domain is extending up and left, down and right forever. That graph is extending forever. So when we look at this graph and we move from left to right and we ask ourselves, what x values does this exist for? This is going up and right forever. So it exists everywhere to the right, and it exists everywhere to the left because this is going down and right forever. So the domain would be all real numbers, -infinity to +infinity.
The range is very similar. We move from the bottom to the top and we think, are there any places where we don't have the graph? Well, this extends down forever, so it does start at negative infinity, and this goes up forever, so the range is also all real numbers, meaning the domain in interval notation would be negative infinity to infinity, and the range would also be negative infinity to infinity. For letter B, we have one distinct endpoint and one that goes on forever. So when we do the domain does not exist to the left of negative 6, meaning it exists from negative 6. We move right, it exists, it exists, it exists. That goes up and out forever. So that domain will go all the way to positive infinity. And the range, similarly, we start from the bottom, we move up. It doesn't exist until we get to the value y equals negative 2, which is right here. And we move up, and it exists everywhere above that because, again, this goes up and out forever, right? So that would go from negative 2 to positive infinity. Finally, on letter C, this one's tricky, tricky, tricky. For the domain, we're again looking left to right. The graph starts to exist at x equals negative 4, which is a closed circle. And it exists all the way over to positive 2, which is an open circle. Now you may be looking here in the middle and going, hey, there's an open circle right there. Yes, but there's a closed circle down here, which means for x equals negative 1, the function is defined. It does have a value, so it's still only one piece. The domain is all x values from negative 4 all the way up to 2, including negative 4, not including 2. The range is a little bit trickier. As we move from bottom to top, we have these two pieces that need to be strung together. The first piece, it starts at negative 1, which is an open circle, and it moves up to positive 1, which is a closed circle. That's this piece. Then we have the other piece, which we move up. There's no graph between 1 and 3, but it exists at y equals 3, and the entire piece is y equals 3. So we would have to write that as the interval 3 to 3, because it's all y equals 3. So there's your domain and range for letter C. That takes us to the back of the graph, where we're asked to find, or back of the worksheet, where we're asked to find domain and range. So we start off on not domain and range, x and y intercepts, sorry. So the first graph is a quadratic. The x-intercepts are where y equals 0, where we cross the x-axis. There are 2 of them. We have them at x equals negative 2 and x equals positive 1, or the points negative 2, 0, 1, 0. We only have one y-intercept. It's where it crosses the y-axis. That is at the point 0, negative 2. For letter B, the x-intercepts, there's only one. Again, it's a graph. So we have one x-intercept at the x value x equals 3, or the point 3, 0. And we actually have 2 y values, 2 y-intercepts, at the points 0, 1 and 0, 3. Finally, on letter C, we're asked to do the same thing, except we're asked to do it with an equation instead of a graph. So for the y-intercept, what we're going to do is I guess I should do x with red because we'll do it that way. The x-intercepts, we are going to let f of x, or in this case k of x, equal 0. So that would be 0 equals x to the 4th minus 9x squared. That is a factorable binomial. It has a greatest common factor of x squared. So we'd start by factoring out x squared. And then that is a difference of 2 perfect squares. So it would factor again into an x plus 3 and an x minus 3. Zero factor theorem says we have 3 sets of roots there. Either x squared equals 0, x plus 3 equals 0, or x minus 3 equals 0, which means our solutions are x equals 0, which happens twice, x equals negative 3, which happens once, and x equals 3. So we have x-intercepts at 0, 0, negative 3, 0, and 3, 0. For the y-intercept, that's even easier. The y-intercept, we're going to let x equal 0, which means we're looking for k of 0, which would be 0 to the 4th minus 9 times 0 squared, meaning 0, 0, because that equals 0. So the point 0, 0 would be our y-intercept. Okay, that takes us to number 5, which is continuity. We've been struggling a little bit with continuity, so please pay close attention here. On all 3 of these equations, we are asked to determine whether or not the function is continuous at the x value x equals 2. So on a graph, that's pretty simple. We go to the value x equals 2, and we look. And what we're looking for is, do we have to pick up our pencil? And if we were drawing that, the answer to that is absolutely no, we would not. Now I'm going to write this out in limit notation. First of all, the function itself at x equals 2 has a value of 1. So that's the function's value when x equals 2, y equals 1. That's the point 2, 1. The limit, as our x value approaches 2 from the positive side, in other words from the right, see how the function is approaching that value as well, positive 1. And the limit, as x approaches 2 from the negative side, from here, it is also approaching 1. So if you notice, the function's value at 2 is equal to the limit as x approaches 2 from the positive side is equal to the limit as x approaches 2 from the negative side, which means yes, f of x is continuous at x equals 2, and we have proven that by showing this continuity. On letter B, this is a piecewise function. To check continuity at a piecewise function, you need to check to make sure that both pieces, since it's broken at x equals 2, have the same value. Now, the bottom piece is where the function would actually be evaluated at 2. So what we do is we plug in f of 2, and please keep in mind that this is also equal to the limit as x approaches 2 from the positive side, because that's every x value greater than 2, which means 4, 3, 2, right? We're moving in from the left. That is equal to 2 squared plus 1, or 5. The other piece, when we plug into the other piece, we're finding the limit as x approaches 2 from the negative side. That is 2 times 2 minus 1, or 3. So right away we should notice that the limit as x approaches 2 from the positive side is not equal to the limit as x approaches 2 from the negative side. This indicates that it is not continuous, so f of x is discontinuous. At x equals 2, and anytime it's a piecewise function, this is a jump discontinuity. Because again, the right limit and the left limit are not equal. That brings us to the last one, which I really would not say that the third one is the hardest. I'd say the middle one is probably the hardest for you guys because you're not familiar with limit notation. But again, what we do for g of x is we need to factor it completely. So the top factors into x plus 2 and x plus 3. The bottom factors into x plus 3 and x minus 2. So you notice that the values that are not in the domain, x is not allowed to equal negative 3, and x is not allowed to equal 2. So we definitely do have a discontinuity at 2. So we would say f of x is discontinuous at x equals 2, because that's not a value that's included in the domain. But we need to figure out whether that is representative of an asymptote or a hole. So what we need to remember is that when it's factored, if the factor that's causing it will cancel like x equals 3 does, that is an example of a hole, which would be removable discontinuity. However, x minus 2 does not cancel, which makes it an asymptote and makes this infinite discontinuity. So once we know it's discontinuous, we have to figure out how it is discontinuous. In this case, it is an asymptote, which is infinite discontinuity. Okay, I believe number 6 is the last problem. We're asked about the end behavior of the following function. We need to remember that end behavior mostly is notation that is always the same. So we're looking at the left end behavior, which is the limit as x approaches negative infinity of f of x. And we're looking to see what does the function do when we go to the left, the function goes up. So the limit as x approaches negative infinity, the function goes to infinity. As the function approaches positive infinity, which is the right end, notice that the function is going down forever, meaning the limit as x approaches infinity is negative infinity. There's your end behavior for letter A. On letter B, please note they're not trying to trick you here. You'll notice that on both ends we are approaching a very specific value. Okay? We have these horizontal asymptotes on this graph. So most of the notation is the same. The limit as x approaches negative infinity of g of x is the behavior on the left end. As we go left, the function is approaching this dotted line, which is positive 1. The limit as x approaches positive infinity of g of x is the right end. So as we go, x goes up, this function is approaching this bottom dotted line, x equals negative 3. So there's our end behavior for the second one. The third one requires a certain amount of knowledge of algebra. We need to know that this is a quadratic, meaning a parabola, and that a is negative, which means that that parabola opens down. That's really all we need to know. We don't care where it crosses the x-axis. We don't care about anything other than its basic shape. Because again, that tells us everything that we need to know to state the end behavior. So we're going to call this h of x, I think is what I did in the notes. The limit, as x approaches negative infinity of h of x, this function as we go to the left points down to negative infinity. And the limit as x approaches positive infinity of this function, as we move to the right, the function is also pointing down to negative infinity. That's it for the review. Thank you for your attention. Good luck on your quiz tomorrow.